Hi friends, welcome to my blog ECG Basics. Today we will discuss about the cardiac axis. Cardiac axis is basically the net current direction of the cardiac activity, that is the sum of both positive and negative deflection, and it represents the sum of depolarization vectors generated by the individual cardiac myocytes. Clinically, it is reflected by the ventricular axis, and interpretation relies on determining the relationship between the QRS axis and the limb leads of the ECG. Since the left ventricle makes up most of the heart muscles under the normal circumstances, normal cardiac axis is directed downwards and slightly to the left, and normal axis is between minus 30 degree to 90 degree. As we have already discussed in the previous blogs that precordial leads are V1 to V6, lead 1 and AVL, and V5 V6 are lateral leads, lead 2 3 AVF are inferior leads, and lead AVR is right sided lead, or we can say that it sees the cavity of the heart, or it is against the in the direction opposite to the net direction of the vector. For axis calculation we use the quadrant methods, and most commonly we use two leads which are perpendicular to each other, that is lead 1 and lead AVF. We can also use lead 2 and AVL and lead 3 and AVR, but most of the practitioner they use lead 1 and AVF for the axis calculation. We use the quadrant method for axis determination. Suppose this is the x-axis and this is the y-axis. The lead 1, as we see, it is in the direction of it is in this direction, we call it as a lead 1, and AVF is in the direction of lead, or we can say y-axis. Lead AVF is in the direction of y-axis. Similarly, if the direction of the lead 1 is axis in the lead 1 is like this, and direction of the vector in lead AVF is in this direction, this direction will be depicted by lead minus lead 1, and this will be depicted by minus lead AVF, because direction of vector is opposite to the direction of AVF. That's why we are writing minus AVF, and the direction of this is opposite to the direction of lead 1. That's why we are writing it as lead minus 1. If we see the coordinates will be positive, because x-axis is positive, y-axis is also positive. Here the x-axis is positive, y-axis is negative. Here x-axis is negative, y-axis is positive. Here both are negative. If we say this is quadrant 1, 2, 3 and 4, means if the lead 1 is positive and AVF is also positive, we will represent it like this. If lead 1 is positive, AVF is negative, it will be represented here. If lead 1 is negative and AVF is positive, activity will be represented in this quadrant. And if lead 1 is negative and AVF is also negative, then the electrical activity or the cardiac axis will be represented in this quadrant. So if we see that if lead 1 is positive and lead AVF is also positive, then the electrical activity or the cardiac axis will be in this quadrant and it will be directed like this. And if lead 1 is positive and AVF is negative, then the direction of the vector will be like this. If electrical activity lead 1 is negative and AVF is positive, then the direction of the vector will be like this. And if both lead 1 is negative and lead AVF is also negative, the direction of the vector will be like this. So when the lead 1 is positive and AVF is positive, the direction of the vector is in this direction, that is towards a main left ventricle. Okay, so this is the normal axis of the heart. Normal axis of the heart we say when lead 1 is positive and AVF is also positive. If there is deviation of this axis towards the left, we call it as a left axis deviation, and if deviation of the axis is towards the right, we call it as right axis deviation. In this diagram we can see that the lead 1 is positive, lead AVF is also positive. So we have to draw the quadrant like this. Lead 1 is positive, lead 1 is positive, AVF is also positive. So this will occupy this quadrant. The direction of the axis will be like this. This is a normal axis. Normal axis is usually between -30 to 90 degree. As I said, that axis calculation can be done from lead 1 and AVF, lead 2 and AVL, lead 3 and AVR. Means we usually use those leads which are perpendicular to each other. Most of the practitioners, they use lead 1 and AVF, and this is more easy for axis calculation. So we saw in the previous slide that this quadrant is the normal axis, and I told that normal axis lies between -30 to 90 degree. This is plus 60 degree, plus 90, and this is 120. This whole area is covered by the normal axis. So for axis calculation, we have to use lead 1 and lead AVF. Lead 1 and AVF, we draw the plot. We draw a quadrant and we see the position in which quadrant the axis lies. Okay, we will apply this method in subsequent slides. Here in this diagram, what we see is this is the normal axis and this is the left axis. This whole area is covered by the left axis deviation, because, and this area is right axis deviation, and this is extreme axis deviation. Before discussing this diagram, let us come back to the previous slide. As I said, when lead 1 is positive and AVF is also positive, that will be a normal axis. When lead 1 is positive and AVF is negative, then it will be a left axis deviation. When lead 1 is negative and AVF is positive, then it will be a right axis deviation. When both the lead 1 and AVF are negative, we call it as a extreme axis or northwest axis deviation. Now this lead this left axis deviation is usually of categorized into two: physiological left axis deviation and pathological left axis deviation. Now, how we say whether it is a physiological or pathological? Since we know that lead 1 is negative, AVF is lead 1 is positive and AVF is negative. Lead 1 is positive, AVF is negative. Now we have two options whether to say it as a pathological or a physiological. We call it as a physiological only. We have to see the lead 2 also. If the lead 2, the net direction of the QRS complexes is, if it is positive, then we call it as a physiological LAD, left axis deviation. If the net direction of the QRS complex in lead 2 is negative, then we call it as a pathological left axis deviation. We have to see lead 1 AVF. If lead 1 is positive, AVF is negative, we call it as a left axis deviation. Now we have to see whether it is a physiological or pathological. For this we see lead 2. If the net direction of the QRS is positive, then we call it as a physiological axis deviation. If the net direction of the QRS complexes in lead 2 is negative, we call it as a pathological left axis deviation. So here we see that lead 1 is positive, lead AVF is negative, means lead 1 is positive, AVF is negative. Then we have two options whether it is a physiological or pathological, but here the lead 2 is negative. So when the lead 1 is positive, AVF is negative, that is left axis deviation. If we have to see lead 2, if it is negative, then it is a pathological left axis deviation. Now in this case, lead 1 is positive, lead AVF is negative, this is left axis deviation. We see lead 2 is positive, then we call it as a physiological left axis deviation. So the normal axis is lead 1 is positive, AVF is also positive, this is a normal axis. So normal axis will be from this normal physiological left axis deviation plus normal axis, from minus 30 to plus 90. This is the normal axis. Here we see lead 1 is negative, lead AVF is positive, this is the right axis deviation. Here both the lead 1 and lead AVF are negative, this is indeterminate axis, or we call it as northwest axis. One mnemonic is useful to see whether it is a left axis deviation or right axis deviation, that is left leaves, right reaches. Means here if we see direction of the lead 1 is and lead AVF, they are in opposite direction, means they are moving away from each other, left leaves. And for right axis deviation, here the net direction of the vectors is, if we see lead 1 and AVF, lead 1 is moving like this, AVF is moving towards this right reaches. Here left lead 1, AVF, lead 1 is moving like this, AVF is moving like this, so they are moving away from each other, left leaves, right reaches. This mnemonic will help us to determine the axis Left leaves means left axis deviation. We have to see lead 1 and AVF. Right reaches means we have to see lead 1 and AVF. If their uh, vectors are moving towards each other, means reaching each other, we call it as a right axis deviation. So for axis calculation, once again I will tell you to remember this mnemonic: left leaves and right reaches. We see lead 1 and AVF. If lead 1 is positive, lead AVF is negative. We can see the direction of the vector, they are moving away from each other. This is the left axis deviation. And if lead 1 and lead AVF, if the direction of the vector is lead 1 is negative and lead AVF is positive, the direction of the vector is like this, they are coming towards each other. This is the right axis deviation. And again, for left axis deviation, always look at lead 2. If we get positive QRS complexes, then it is a physiological left axis deviation. If we get negative net QRS complexes, that is a pathological left axis deviation. We can also remember this table for axis calculation. If lead 1 is positive, as I discussed in the previous slides, lead AVF is positive, that is a normal axis. For lead 1 is positive, lead AVF is negative, then it is left axis deviation. Look at the lead 2. If net positive vector in not net positive QRS complex, we call it as a physiological left axis deviation. If we get net negative QRS complex in lead 2, then we call it as a pathological left axis deviation. If lead 1 is negative, lead AVF is positive, then this is a right axis deviation. And if both are negative, we call it as extreme axis deviation. Please remember this table. So this is what I told for left axis deviation, that it can be physiological or pathological. We have to look at lead 2. If net vector in net QRS vector is positive, we call it as a physiological, and if net vector is negative, we call it as a pathological LAD, left axis deviation. Remember important causes of left axis deviation as left ventricular hypertrophy, left bundle branch block, inferior MI, Wolff-Parkinson-White syndrome. Wolff-Parkinson-White syndrome basically shows both left axis deviation and the right axis deviation. Then we have ventricular pacing or ectopy, left anterior fascicular block. Extreme axis deviation is seen in ventricular arrhythmias like ventricular tachycardia, AIVR, ventricular ectopy, hyperkalemia, or right ventricular hypertrophy. Similarly, causes of right axis deviation are the right ventricular hypertrophy, chronic lung disease, COPD. In COPD, the heart becomes tubular. Hyperkalemia, renal insufficiency, dextrocardia, Wolff-Parkinson-White syndrome, ventricular ectopy, and many more causes which you can remember. If we see this ECG, the lead 1 is positive, AVF is negative. So this will be a left axis deviation. And if we see the lead 2, the net direction of the QRS complex is negative. So it is a pathological LAD. Similarly, in this ECG, lead 1 is positive and AVF is negative. Again, it is a left axis deviation. Now we have to see lead 2. Net QRS direction is negative. So it is again pathological LAD. In this ECG, lead 1 is positive, lead AVF is positive, lead 2 is also positive. So if we see the quadrants, lead 1 is positive, lead AVF is negative, sorry, lead AVF is negative, lead 1 is positive, so direction of the quadrant is this. This is left axis deviation. We have to see now lead 2. In lead 2 net direction of the QRS complexes is positive. So when the if we have left axis deviation and the lead 2 shows positive deflection, or lead 2 has a positive net vector, we call it as a physiological LAD. If we see this ECG, again lead 1 is positive, lead AVF is negative, means left leaves, lead 1 is positive, AVF is negative. Again it is a left axis deviation. We have to see the lead 2 here. If we see we find a net positive deflection in lead 2, again it's a physiological left axis deviation. In this ECG we see lead 1 is negative and AVF is positive. Lead 1 is negative, AVF is positive, so this is a right axis deviation. I hope axis deviation calculation is better understood now. You can read standard books for ECG which I have already mentioned in my previous blogs. Thank you.